Hey everybody, okay, so we're going to go over section 12.5. This is the longest section in the chapter, so please bear with me. It's just a lot of definitions, mainly because we're going to learn how to define random variables, mean, variance, and covariance like it says, but within this section there's discrete random variables, continuous, so there's a couple different sections. We're pretty much just going to look at examples and their solutions already typed out just to save time. And then at the very end, we'll do, at the very end of the section, we'll do one practice problem together. So please just follow along. We're going to go through the definitions. So basically a random variable, it's a function that associates a number with each point in an experiment sample space. So usually, oh my God, I forgot a parenthesis here too. What's wrong with me? We always refer to these in bold-faced capitals. So if you look below, so this is a random variable can be discrete, continuous, but basically it's just a number. It's like a point on each function. Discrete random variables is characterized by the fact that the probability is big X equals little xi, or this is going to be what you see most of the time throughout this section. It's a random variable is discrete if it can assume only discrete values. So only is the big key here. Think of discrete, if you remember back from STA 2023, it's stuff we can count. How high can you jump, or how many people visit an establishment in this closed interval of time. That's a countable thing. Continuous would be something that we can't count, or it is continuously being counted. So probability mass function, or PMF, is what you'll see a lot of the times. All that is, like I said above, is this function here. It's all the masses of the probability function. So the cumulative distribution function, or the CDF, is actually a real function, f of x, and it's for a random variable. So we have CDFs only associated with random variables, and it's basically the same thing as what we saw above, but it's an actual function, and it's an inequality. So if you look below, for any random variable, there are a bunch of different probabilities, right, for each point on that function. So we can the cumulative distribution function sums all of those probabilities up into one function. So this example in the photo may make it a little more clear. So if x is the number of dots shown when we toss a die, the i's would be 1, 2, 3, 4, 5, and 6, because those are all the possibilities we could have, or outcomes. And so for every single one of these points, x has a 1/6 chance of it showing. So they all have an equal chance of showing us. And then this figure below is actually showing us the different probabilities in the function form. So it moves up every time. So if you notice that 5 is all the way up at 5 out of 6, 6. So you're adding on every time. This would basically this is a representation of this, essentially. It's the sum of all of them in one continuous function. So then you guys keep hearing me talk about continuous random variables. These we can't assume discrete values for. So look, if you notice, it says it can assume all values on the interval. So that's why it's continuous. We can't count it because it could assume all the values on the given interval. And then for continuous random variables, we have something called a probability density function, so a PDF instead of PMF. So these are statements about continuous random variables only, and we actually still need to know its probability density function for this. So we actually use the fundamental theorem of calculus to help describe this phenomenon. If you guys remember, this is the part from the beginning. A and B, think of those as certain probabilities, or values on the interval. The random variable can assume all those values, but it just has to be on the given interval. And so if we take our PDF function, little f of x, and integrate it, we actually get the big f of x function. So if you see, we have the corresponding probability to the area under the continuous random variables PDF. So not the CDF like up here. The CDF is continuous for random variable x with a density f of x. So little f of x refers to the density here, or the PDF, and the CDF would be big f of x. So that is very important to remember. And then if you notice here, it says f of a. So if we have a certain probability we're looking for, and we only have 1 point on the interval, maybe it's continuous. If you notice here, we have negative infinity. We are allowed to do this because it is a continuous variable. You would just evaluate for negative infinity. It probably doesn't happen that much, at least for this textbook. So here's an example of what a density function looks like. So consider a continuous random variable x having a density function f of x. So this is the little PDF function from above. And they always give us these parameters. So this is its PDF if it's, it's non-negative in between 0 and 1, because probabilities can't be larger than 1 and they also cannot be negative. So it's 0 if there's anything else going on. So if we get a negative probability or density, we can't have a negative density because there's no chance that we'd get a negative probability, so it's 0. So they want us to find the CDF for x. So basically, to get the CDF, so we integrate the PDF to get the CDF. So, and the PDF, remember, from above is the little f of x, and we want to get the big f of x. Oh, left off a parenthesis again, so sorry. So they want us to also find, in addition to the CDF, they want us to actually use that CDF to find the probability that our continuous random variable is between 1/4 and 3/4. So this would be my A and my B. So it's basically the same thing as fundamental theorem of calculus. A is greater than 0. It's f of A equals 0. True. So for this interval, we go from 0 to A, because we're not yet finding the probability above. We just have to do this to find the CDF. So fundamental theorem of calculus, we put in our function, our boundaries, and to integrate, we would get x squared, and then if we plugged in a, we would get a squared. And then if you plug in 0, we would be getting nothing. So now we can use what we have here to find any probability for this continuous variable, but the probability we need to find is between 1/4 and 3/4. So these just become the boundaries. We still use the same PDF function we're given above, and we integrate like we did before to x squared, and we just plug in our boundaries for this experiment, and we end up with 1/2. So pretty straightforward. Just remember PDF, integrate to CDF, or use fundamental theorem of calculus to get there. So then moving on from just the probabilities of random variables, we're now going to talk about mean and variance. Maybe you don't remember, most of you may not remember variance as well, but you definitely remember the word mean. If you think of mean, it's like an average. But basically for a discrete random variable, the mean and this is of a discrete random variable, is basically just the summation of all of the probabilities of that random variable, multiplied by the values of the random variable. So the mean of a continuous random variable is a little different. Do you notice how this is a sum, right? Because I can count discrete variables, but this has to be an integral from negative infinity to infinity because it's continuous. And all that's changed is, from the fundamental theorem of calculus, is now we're multiplying by all of the points of this continuous random variable, or of the function. So when we're computing E of x, or the mean, each possible value of a random variable is weighted by its probability of occurring. So weighted, that's where the like density functions come in and the mass functions. Now we're talking about the mean. So for a function h of x, of the random variable x, we have the random variable x squared and e to the x and expectation of h of x. We can find all of this, if it's a discrete random variable, by summing the function h of x with all the values of that function and the probabilities of all those continuous random or discrete random variables. And then below, if you notice, for continuous random variables, it is essentially the same representation, but we must integrate these because it is a continuous function or continuous variable. So that's mean is pretty straightforward. If you know, we would just be plugging in the values that we have to these in solving. Variance of a random variable is a little bit different. So it's written as var x, and it measures the spread or dispersion about e of x. The var x is defined, so it's basically the random variable minus its expectation of x, and the whole thing squared. So this will become more clear when we start talking about discrete and continuous. For a discrete random variable, this equation above would yield, essentially, if you notice, all we've done is plugged in this to the summation of all of the random variable values. And for continuous, again, pretty much the same. We're just multiplying that function by our PDF and integrating. And var x can also be found from this relation. This is really important. So you might already have the information in order to go about this. E of x is the probability of the discrete random variable happening. And if you notice, the x squared is on the inside here, but it's on the outside over here. Standard deviation, probably have heard that word before too. So for any of our random variables, the square root of var x is the standard deviation. So the symbol that you probably always see is that little sigma. And discrete random variables, here's an example of how we would be using this to solve for var x and the mean. So consider the discrete random variable x having p of x equals I equals 1, 6, for I equals 1, 2, 3, 4, 5, 6. So this is kind of the example we did way back. They want us to find e of x and var x. So we're just going to take the formulas that we have above. So for e of x, we all remember, for a discrete random variable, we are just summing all of the values of the discrete random variable and its probabilities. Here we go. So 1, 6, if we recall, they all have this, or this is the probability of this of each value of I. They have equal chance of happening. And then here, these are just all of our x's, or i's, essentially xi's. There we go. And so if we multiply that all together, we would get 7 halves. So not too bad. It's literally just the summation of every xi times the p, or the probability of that xi occurring. And then for var, it's a little lengthier, but basically, if we recall from above, for discrete random variable up here, we have the summation of x sub k minus e of x squared, and then multiplied by that probability of the random variable occurring. So this is my like p of x equals I right there. And then the rest of this is that or x minus e of x squared. So x here, if we notice, we have every single 1, 2, 3, 4, 5, 6. And every time I subtract 3.5 from it, and I square it, and I would get 35 over 12. Okay, And then continuous random variables. So find the mean and function, or find the mean and variance for the continuous random variable x having the following PDF. So our little f of x is PDF, again, 2x, and it has to be between 0 and 1 for this to be dealing with probability. To find e of x, remember, for continuous, we just integrate and multiply by our x. So you'd get 2x squared here, and that would eventually be integrated to 2x cubed over 3. We'd get 2/3. Next, for var x, essentially very similar, except we're subtracting the, if you look up here, var x is x minus e of x, and we found e of x above. So that's where the 2/3 come in. You square it, and you multiply by the same PDF. We would have to integrate all of these individually, like happens with the brackets. Plug in 1 and 0. 0 would usually yield 0. And that is the answer. So those are, again, just plugging into the formulas. Independent random variables. Okay, so now we're talking about random variables, but independence, if we have two sets A and B, x is in one, or we have two random variables, one is in A, one is in B, and the probability of both of them is equal to 1 multiplied by the other. X and Y are independent. They have to be independent if the knowledge about the value of Y does not change the probability of any event involving X. So basically, if one occurs or I know about it, it shouldn't affect the other if they're independent. So this is also a good way, oops, thought that was a highlighter. This is also a good way to check because if you multiply them together before and find the probability, it should be the same as if you did them separately and multiplied them together. So covariance, similar to variance, but now we're doing with covariance. It's for two random variables. So before variance, we could just do var x. Now, if we have two variables that we're trying to deal with, it's also written like this. We would define it by the one random variable minus e of that random variable minus, or times y times e of y. Sorry, that's a parenthesis again. So for the value of covariance matters though, that we didn't talk about this with variance before, but for covariance, it's very important. So if it's positive, it will be positive if x or y is greater than its probability. So I put the or in there because it's the same for each variable. So like x goes with e, so x would be greater than e of x, y would be greater than e of y. So if the discrete random variable is already larger than its probability, then that does not work, or it would be positive. And then it's negative if they are less than. So you can kind of check yourself and your work with these rules. And then if they're independent, it would be 0. So this right here, I'm going to star that because that's very, very important. Because, you know, that helps you with certain formulas, knowing which one to use if they're independent or dependent. So this example is going to show us how we actually use all of these things. Each summer in Gotham City is classified as being either a rainy summer or a sunny summer. The profits earned by Gotham City's leading industries, the hotel and the umbrella store, depend on the summer's weather as shown in the table below. All of the summers, 20% are rainy, 80% are sunny. Let h, or discrete variable h and u, be the following random variables. So this is for the hotel, u is for the umbrella store. And they want us to find the covariance of the two. So this table below, this is their CDF. So normally I know we're given like the f of x with a little bracket, but this, since it's profits, this is basically what happens when it's rainy. This is what happens when it's sunny. So we're going to use these values throughout the problem. So we find that E of H is 0.2 times 1,000 plus 0.8 times 2,000. So this is the same thing. This is the probability of it being, let's see, 20% rainy times negative 1,000. Well, that makes sense because it's for the rainy part. And then plus the hotel profit when it's raining. So that would give us the actual full profit in general. Same thing for U. But 0.2 and 0.8 are the same in both of them. So with probability 0.2, that means we had a rainy summer. So we're using the covariance formula from all the way up here. So negative 1,000 is just our regular variable, minus 1,400. That is what we found up here. 4,500 is from the table, and 500 is from our calculation above. And that yields us with $9,600,000 squared. And now we have to do it for when they have a sunny summer. Sorry, this says rainy, but if you guys remember, 0.8 is for sunny. Sorry about these typos. Let me fix this. Sunny. Okay, so it's the same process we did before. We're taking the discrete random variable values from the table, and we're subtracting our probabilities up here from it to get negative $600,000 squared. So now we can actually put this all together for covariance. So if you notice, we had to find the covariance for each probability before we put it all together. So now we just take for the rainy summer and the sunny summer, and we multiply it by the probabilities for the rainy and sunny summer. So we ended up getting a negative covariance, which means it indicates that one industry is doing much better when the other is doing poorly. So that should be an H. So that's a good problem because it's probably more in tune with what we're used to doing in this book. So now, lastly, we're going to do the mean covariance and variance for sums of random variables. So sometimes we have random variables added together, if you notice right here. So we often create new ones. So if we have two random variables, we could multiply them from some constant or add them together to have different variables. And they are going to be expressed in E and var and covariance. So these would be the formulas for certain cases. I'm not going to go through every single one of them. It depends on what the problem is. So like, let's say it says like 4x1 here. Well, then the only difference is that you're multiplying it by that. That's about it. These are important. We'll see in the later examples. So if they're independent random variables, if you notice here, I literally can just split it up, kind of like distribution a little bit. But in general, if I do have them added together, if they're not independent, you have to have the covariance at the end. And then for random variables, I have to have the var of every single variable that or value it would take on plus the summation of the covariance of these two variables. And then constants. So if you notice here, they just pulled both constants out to the front and multiplied by. This is an important rule. I think it actually gets used pretty often. So here's an example to help us understand what's going on. If I pay $1 to play the following game, I toss a die. I receive $3 for each dot that shows. Determine the mean and variance of my profit. So X is going to represent the number of dots, and my profit is going to be the value given 3x minus 1. So if you think about it, $3 times the amount of dots you win, and then you have to pay $1 to play every time. So you subtract $1 from your earnings. So from example 7 way back when we found mean and variance, we're just going to use those values again for our E of X and var of X. And then we're going to use 7 and 8. So like I said, we are going to use some of these formulas. There's a constant in ours, 3x, and then we also have a constant being subtracted. So we're going to need those top two rules. So we know that E of 3x minus 1, well, we can bring out any of the constants that aren't attached to the variable. And then we can also bring out the constant out front and just multiply it by our mean. And that's how you get 19 halves. So then for var, we're going to use 10 and 11 up here and to deal with the constants we have. So we just have to pull out first, or a var of just a constant it goes away, it's 0. We really only care about what's attached to the variable, so that's why it disappears. And if you take a constant out, you have to square it, and then you just multiply it by the actual variance. So not too bad. Again, plugging and chugging. This problem is going to be more in tune with the types of problems we've been doing, or have done throughout this book. It's going to be a lot about if we don't have enough stock, what should we do? This will probably come into play when we're ordering stuff. So I have 100 items of a product in stock. The probability mass function for the product's demand is D. So our random variable is capital D. And so the probability of D equals 90. So when it's 90, it is also the same for D equals 100 and 110. So we have an equal probability of D being those three values, which is 1/3. We must find the mass function, mean, and variance of the number of items sold, and find the mass function, mean, and variance of the amount of demand that will be unfilled because of lack of stock. So that's a lot. Let's start with A. So we're going to have to define a few things. I'm going to say S is the number of items sold. Okay, and then P of S equals I is basically just the PMF for our random variable S. If you remember PMF from way back in the beginning of this video. So they told us above though, right, that they're all 1/3. For I equals, okay, they told us this was for 90, 100, and 110. Okay, so this is just the proper way to start writing the problem for the PMF. And the number of items sold cannot exceed 100. So yes, we have 110 here, but we only have 100 items in stock. So we need to keep that in mind. So the mean number of items sold, so for a discrete random variable, if we remember, the mean is just the summation of all of the i's times P of I. Okay, so if you think about it, right, I have 90, 100, and 110, and I multiply them all by 1/3. Okay, and that is going to give me, I'm just going to take the 1/3 out actually, and 90 plus 100 plus 110 is 290. Sorry, I cannot add. No, actually, I'm sorry. It is 300. Because 90 plus 100, 190 plus 110 is 300. Okay, sorry about that. So E of S is 100 in this case. Perfect, that worked out really nice. Okay, so now the variance var of S is again another summation. If you notice, that is the way we do discrete variables. And for that, it's just S, like the number of items we have, subtracting the probability of them, or the mean of them, and we square it and multiply it by the probability of S equals I, which was our 1/3. So I'm just gonna have the 1/3 out front because it'll be a little long. So right, we have to have 90 minus 300 squared plus 100 minus 300 squared plus 110 minus 300 squared. And this would be 1/3 times, let's think about this. I would have sorry guys, 210 squared plus 200, or negative, these are all negative, but that doesn't matter because they will become positive, and 190 squared. Unfortunately, I do not know the answer because I don't have my calculator with me. I'm going to pause this really fast and I'll come back. And with the correct answer, just bear with me. Okay, guys, so I did it out on my calculator, and 120,200 does not divide by 3 perfectly, so I'm just going to leave it as a fraction for the time being. So let's move on to B. We're going to let U be the number of items unfilled because of the lack of stock. So U equals unfilled items. Okay, so that means that P of U equals I is the PMF for U. Okay, so we need to do a little bit of calculating, but basically we have to calculate our I's because I is actually, it's the items not filled with stock. So, let's think about it. So we have 90. Well, 90 can be filled. So we have 0 as our first I. For 100, we have 100 minus, we have 100 items in stock. So that's also 0. And then 110 minus 100, though, we don't have all those items in stock. That is 10. So P of, oh my God, I don't know what that is. I'm sorry. P of U equals I is 1/3, like they told us above, and it's 4 different i's now, though. So it's I equals 0, 0, 10. And we do have to have 0 twice here. It's just proper etiquette, but it also doesn't matter because it's 0, but because it happens twice. So to do the mean number of items unfilled, again, we're just going to do the summation of it. That same formula we had before where we have I times P of I, which would be 1/3. I'm just going to write it all out times 0 plus 0 plus 10, which would yield 10/3. So that's the mean of all 3 cases. So now variance is just a little bit longer. So the variance is the summation. That is ugly. I will rewrite that. Summation of U minus the mean squared, and we multiply that all by the probability of U equals I. And so that means I'm going to have 1/3 out front just to start with 10/3 squared. If you notice, it's by itself because it would just be 0 with it, and that doesn't matter. 0 minus anything, it doesn't really matter. And then plus 10 minus 10/3 squared. And that would give me 1/3 times 100/9 plus 100/9 plus 400/9. Okay, so now we have 1/3 times 600/9, which would give me, if we simplified this, that'd be 203. So I'd get 200/9 as my final answer for that. So that's the answer for B, and this was also one of our answers. And same thing for up here, we have variance and we have our mean. So again, straightforward. All we basically are doing is plugging into our formulas. So thank you guys for staying with me for the long section.